The history of the Second World War is often recounted in the deafening vernacular of heavy artillery, the rhythmic grind of tank treads, and the desperate roar of bomber engines overhead. We recall the grand strategies and the monumental clashes, Kursk, Midway, Stalingrad. These visible convulsions of military power defined the epoch. Yet, beneath this spectacular violence, another war was waged, a silent conflict fought not with steel and fire, but with mathematics, chemistry, and ingenuity. This was the war of the workshop, the laboratory, and the quiet, flickering glow of the draftsman's lamp. The true pivots of history were often unassuming objects: a simple pressed metal container, a microscopic mold, a small electronic tube. These 5 silent catalysts lacked the spectacle of a newly unveiled battleship, but they possessed the quiet power to reorganize entire campaigns, preserving life, extending supply lines, and ultimately charting the trajectory toward Allied victory. They were the essential, often overlooked, mechanisms grinding beneath the massive, unrelenting engine of global conflict. Our first journey into the architecture of quiet change takes us to the desolate, shimmering heat of the North African campaign. Here, warfare was a grueling test not just of men and machines, but of logistics, the very lifeblood of a mobile army. The armored thrusts that Rommel championed and Montgomery eventually mastered were utterly dependent on their ability to travel vast, waterless distances across sand and scrub, perpetually outpacing their own supply lines. The common impediment to these sweeping maneuvers was not enemy fire, but simple, debilitating thirst for the vehicles. Gasoline was the desert's most precious commodity, and the failure of its container could spell doom for an entire mechanized column. Before 1940, the British and American armies relied on flimsy, often leaky, 20-liter petroleum tins, known colloquially as flimsies. These square tins were cheaply made, soldered together, and possessed thin metal walls prone to rupture or puncture when jostled over rocky ground or carelessly thrown from a supply truck. They stacked poorly, oxidized quickly, and required a specialized tool, a spout or funnel, to pour without spilling precious fuel into the thirsty sand. The resulting waste rate was catastrophic, sometimes reaching 20 or even 30% of the delivered payload before it ever reached the engine. Mobile warfare in the desert, under such conditions, was a statistical nightmare. Every mile gained was a logistical gamble, fueled by waste. Then, captured by chance during the initial skirmishes, the Allies discovered the German answer, the Wehrmacht Einheitskanister, universally known to the world simply by its Allied nickname, the jerry can. This object was utilitarian poetry in steel. Weighing 10 pounds empty and designed by the engineer Paul Pleiss in 1937, the jerry can was a marvel of robust, intelligent design. It was fabricated from heavy-gauge steel, welded rather than soldered, and featured a distinctive 3-handle design. This trio of handles allowed a single man to carry 2 empty cans with ease, or 2 full cans, or allowed 4 cans to be passed quickly by a chain of men. Crucially, the handle system was recessed, protecting the wide cam lever locking cap. The true genius of the jerry can, however, lay in its internal engineering. It was lined with a fuel-resistant material to prevent corrosion and flaking that could clog filters. It featured an internal air channel that ran from the base of the can to the pouring spout, allowing air to enter as fuel exited. This ventilation meant the 20 liters could be poured out smoothly, without glugging or splashing, often in under 7 seconds, and without requiring a funnel. Most critically for the desert environment, the can was designed with a small air pocket built into the structure, allowing the fuel inside to expand under intense desert heat without warping the sides or bursting the seals. The jerry can was an airtight, durable, perfectly balanced logistical tool. The impact was immediate and profound. When Allied forces, led by American manufacturers, reverse-engineered and mass-produced the captured design, the logistical bottlenecks of the Desert War began to dissolve. Fuel waste dropped to negligible levels. Supply convoys could move faster and more reliably. The quiet adoption of this superior metal box guaranteed that Patton's sweeping armored thrusts across Sicily and into France, and the long, brutal supply lines sustaining the entire North African campaign, did not die from infrastructural thirst. The jerrycan was not a weapon, but it was the silent logistical foundation on which the greatest mobile offensives of the war were built. While the jerrycan preserved the fuel that kept the machines running, a microscopic marvel manufactured quietly in vast vats preserved the fighting strength of the men inside them. The introduction of penicillin during the war fundamentally redefined the brutal calculus of battlefield survival, changing catastrophic wounds from near-certain death sentences into recoverable injuries. Before the mid-1940s, the greatest killer of soldiers was not the bullet or the shrapnel that inflicted the initial wound, but the subsequent infection. A minor perforation could turn septic within days, leading to gas gangrene, tetanus, or systemic blood poisoning. Treatment was often crude and agonizing: aggressive debridement of infected tissue, draining abscesses, or the desperate final resort of amputation. The smell of a field hospital in the early war years was a sickening mixture of blood, carbolic acid, and the sweet, putrid scent of rotting flesh. Mortality rates for compound fractures or deep abdominal wounds were astronomical, often exceeding 50%, crippling the effective manpower of any deployed force. Though Alexander Fleming had first noted the bacteria-killing properties of the penicillium mold in 1928, it remained an academic curiosity, difficult to isolate, chemically unstable, and impossible to produce in quantity. It was the frantic effort led by Australian pathologist Howard Florey and German refugee biochemist Ernst Chain at Oxford University that cracked the code of stabilization and purification in the late 1930s. Their early experiments, showing that a few drops of the purified mold juice could save mice injected with lethal bacteria, confirmed they had a chemical weapon against disease, unlike any known before. The challenge of scaling production was insurmountable in wartime Britain, constantly under the threat of Luftwaffe bombing. Florey and his colleague Norman Heatley brought their research to the United States in 1941, literally carrying the mold spores in tiny bottles on a transatlantic flight. This moment marked the true beginning of the American industrial war effort against infection. Under immense pressure and with critical government support, U.S. pharmaceutical companies like Merck, Pfizer, and Squibb, working in fierce and patriotic collaboration, transformed the production process from flask-based surface culture, producing tiny quantities, to deep tank fermentation, producing industrial volumes. The scaling was a biological engineering miracle. Vast, sterile vats, sometimes holding thousands of gallons of nutrient broth, mostly corn-steep liquor and lactose, became the silent battlefields where the penicillium mold quietly waged war against the unseen enemy. The goal was to produce a stable, dry powder that could be stored and administered anywhere. By 1943, mass production was underway, reserved almost exclusively for military use. The sensory impact of penicillin's arrival in the field was immediate and transformative. Medics, previously forced to helplessly watch patients spiral into septic shock, now held a small glass vial containing a white, crystalline powder. Administered via injection, the antibiotic would rush through the bloodstream, systematically halting the bacterial invasion. Wounds that would have necessitated a limb removal could now heal, sometimes dramatically, within days. The dreaded smell of gangrene began to retreat from the field hospitals. The recovery tents, though still noisy with the pain of the wounded, began to harbor a new atmosphere of hope. Penicillin was deployed extensively during the pivotal North African and Italian campaigns, and by D-Day in 1944, it was standard issue for every combat medic. Its silent, profound effect was registered not in battle statistics, but in recovery statistics. Allied armies achieved a survival rate for severe wounds, especially those involving deep soft tissue penetration, that was radically higher than that of the Axis powers, who did not gain comparable access to mass-produced antibiotics until much later, or at all. Penicillin conserved the most precious resource of all, human life. By reducing the rate of permanent disability and death, it maximized the available fighting strength, becoming a force multiplier that quietly preserved divisions that would otherwise have been lost to the grim reaper of secondary infection. From the desert floor and the operating table, we ascend now to the cold, echoing operations rooms high above the fog-shrouded English coastline, where the fate of the war was being tracked on flickering green screens. This shift from logistics and biology to physics and electronics saw the invention of the cavity magnetron, a device small enough to hold in one hand, but powerful enough to pierce the oppressive darkness and transform the very nature of detection and navigation. The initial stages of the war, particularly the Battle of Britain, exposed the profound vulnerability of defense forces to surprise attack. While Britain had developed rudimentary radar systems, like the massive, fixed chain home stations along the coast, these operated on long wavelengths, rendering them clumsy, vulnerable to jamming, and critically, unable to be miniaturized for deployment on aircraft or small ships. The long wavelengths also meant they could not accurately distinguish between targets flying close together, or locate small objects, like the periscope of a submerged U-boat. As the Blitz intensified and night bombing became standard, the need for a compact, high-resolution radar became desperate. The key breakthrough came in 1940 at the University of Birmingham, led by physicists John Randall and Harry Boot. They developed a compact, high-power microwave generator, the cavity magnetron. Imagine a hollow copper cylinder, slotted with numerous internal cavities, like a large copper donut with internal rings. When a powerful magnetic field was applied and a high voltage introduced, the electrons orbiting the central cathode were forced into spiral trajectories, exciting the resonant cavities. The resulting effect was the generation of extraordinarily intense pulses of microwave energy, short wavelength radio waves, at peak powers previously unimaginable, up to 10 kilowatts per pulse. This was the quiet revolution. Microwaves, unlike the long waves used by chain home, allow the use of small, dish-like antennae. This meant the entire radar apparatus could be shrunk, fitted into the nose of a night fighter, or placed beneath the wing of a coastal patrol bomber. The high frequency of the microwaves provided exponentially better resolution, allowing operators to distinguish fine details and locate smaller targets with far greater accuracy. The initial impact was felt directly in the skies. Fitted to Beaufighter and Mosquito night fighters, the magnetron-powered Airborne Interception (AI) radar transformed the chilling equation of the night war. Previously, hunting a bomber in the dark was a blind chase based on sound and guesswork. Now, inside the cold cockpit, the radar operator watched the hypnotic green line sweep across the screen, displaying the enemy aircraft as a sudden telltale blip of light, guiding the pilot toward the kill. This ability to see in the dark tipped the scales, making night bombing increasingly perilous for the Luftwaffe. Its second, and arguably more strategically crucial deployment, was against the U-boat menace in the Atlantic. U-boats, forced to surface at night to recharge their batteries, were virtually invisible to the naked eye. When equipped with magnetron-driven air-to-surface vessel (ASV) radar, Allied patrol planes gained the ability to sweep the vast, churning gray surface of the ocean and detect the tiny metallic signature of a surfaced submarine, even in dense fog or pitch-black darkness. The introduction of microwave radar in 1942 turned the tables in the Battle of the Atlantic. U-boat captains, relying on the cover of darkness, suddenly found themselves illuminated by unseen beams. Attacks from patrol planes, often appearing seemingly out of nowhere, caused devastating losses. The German countermeasures were slow and ineffective because they did not understand the frequency the Allies were using. The magnetron had effectively blinded the hunter, forcing U-boats to remain submerged for longer periods, drastically reducing their operational effectiveness and directly contributing to the Allies' Black May of 1943, the month when U-boat losses became unsustainable for the Axis. The magnetron was the silent eye that ensured the crucial transatlantic lifeline of men and material remained open. Down in the depths of that churning gray Atlantic, where the U-boat had been king, another unassuming invention brought tactical parity back to the Allied destroyer fleets. For years, the standard anti-submersion weapon was the depth charge, a large barrel-shaped explosive dropped off the stern of a destroyer, detonated by hydrostatic pressure at a preset depth. The procedure was fraught with inherent vulnerability. As the destroyer made its attack run, it was forced to pass directly over the submerged U-boat to drop its charges.
In the critical moments immediately following the drop, the sub was directly beneath the ship, rendering the ship's primary sonar, which required waterborne sound reflection to function, completely blind.
This meant the U-boat had a precious window of time, perhaps 30 seconds, to maneuver, dive deeper, or prepare a counterattack while the destroyer was deaf and awaiting the distant subterranean thunder of the charge. The kill probability for a single depth charge attack was notoriously low, often hovering around 5%. The solution emerged in 1943 in the form of the Hedgehog. Named for its appearance, a series of 24 small, stubby mortars clustered atop a platform on the ship's foredeck. The Hedgehog was a forward-firing anti-submarine mortar. Instead of being dropped off the stern, the Hedgehog charges were hurled over the bow in a circular pattern, landing in the icy abyss about 200 yards ahead of the ship. The mechanical difference was crucial, but the tactical difference was life-saving. Because the weapons were fired forward, the destroyer could maintain continuous contact with the U-boat via its sonar throughout the attack run.
The cold, tense silence on the destroyer's bridge would be broken only by the rhythmic ping of the sonar tracking the submarine.
The moment of firing itself was distinctive, not a single explosion, but a rapid sequence of 24 silent, high-arc plumes of smoke, followed by the sound of the projectiles splashing into the waves. The operational design was the true game-changer. Unlike depth charges, which relied on proximity and a hydrostatic fuse, the Hedgehog charges were contact-fused. They would only explode upon directly striking the rigid steel hull of the U-boat. This seemingly counterintuitive design decision had two profound advantages. First, if a U-boat was hit, the resulting damage was catastrophic. A direct contact explosion meant a near 100% certainty of sinking. Second, if the charges missed, there was no explosion. This was vital. The sound of a typical depth charge explosion, a tremendous concussive pressure wave, would blind the sonar for several minutes, forcing the destroyer to circle back and restart the hunt. The silent mist of the Hedgehog allowed the attack to be immediately pressed home again if the U-boat was still within range. The impact of the Hedgehog was immediate and dramatic. The probability of sinking a U-boat per attack run jumped from 5% to over 25%. The psychological effect on the U-boat crews was equally powerful. No longer could they rely on the few seconds of safety granted by the enemy's sonic blindness.
The Hedgehog transformed the convoy escort from prey into a highly efficient hunter, marking a decisive shift in the tactical superiority in the closing years of the Battle of the Atlantic. It was a silent, forward-moving weapon that turned the terrifying soundscape of the deep into a death trap for the German submarine force. Finally, we turn our gaze even higher, to the aerial defense, where milliseconds meant the difference between safety and devastation. The high-altitude threat, from conventional bombers, and later from the terrifying, unpredictable V-1 flying bomb, demanded a quantum leap in anti-aircraft AA precision. Traditional AA artillery required an operator to manually set a fuse timer before loading the shell,
estimating the time until the projectile would reach the target's predicted altitude and trajectory. This was a complex, time-consuming, three-dimensional math problem solved by hand under immense pressure. Inevitably, the vast majority of shells exploded harmlessly in empty sky, a towering fireworks display that rarely achieved a kill. The sky needed a smarter weapon.
The answer was the variable time VT proximity fuse, often referred to by the Allies as the secret weapon that won the war. This was an entire miniature functional radar set built into the nose of a standard artillery shell, designed to withstand the immense 20,000 G-forces of being fired from a large cannon.
It was the epitome of wartime miniaturization and engineering genius, comparable in complexity to the magnetron itself.
The fuse contained a tiny vacuum tube-based radar transmitter and receiver, a rugged safety and arming mechanism, and a small, robust chemical battery that activated only upon the shell's firing. Once airborne, the miniature radar pulsed microwaves outward. As the shell neared a target, be it an aluminum bomber skin or a steel V1 fuselage, the transmitted waves would reflect back, generating a signal. When the reflected signal reached a peak strength, indicating critical proximity, the fuse would automatically detonate the high explosive payload.
The VT fuse eliminated the need for human timing and calculation, transforming AA warfare overnight. The shell did not need to hit the target, only come close. Instead of firing an estimated point in space, the AA gunners were effectively throwing a self-detonating cloud of shrapnel around the target. It took the guesswork out of the equation and replaced it with electronic certainty.
The implications for defense were staggering. Against conventional bombers, the lethality of anti-aircraft fire increased by a factor of 3 to 5 times. Flak batteries, previously inefficient noisemakers, became a genuine, terrifying wall of explosive defense.
Crucially, the VT fuse provided the critical defense against Hitler's vengeance weapons.
When the pilotless, pulsed-jet V1 doodlebugs began slamming into London, causing widespread terror and destruction, conventional defense struggled to keep up with the fast, small targets.
Placing VT-fused AA batteries on the coastline created a curtain of lethal explosions through which the V1s could not pass. More than 80% of the V1s directed at London in late 1944 were successfully intercepted and destroyed by AA fire, utilizing the proximity fuse. Furthermore, its naval applications were decisive in the Pacific, particularly against the desperate kamikaze attacks of 1945. Conventional naval AA fire struggled to hit the fast-diving, erratic Japanese planes. The proximity fuse turned the deck guns into lethal point defense systems. As the suicide planes screamed toward the fleet, they were met by continuous, exploding shrapnel that tore wings and tails off aircraft hundreds of yards away from the direct line of fire, saving countless ships and the lives of thousands of sailors.
The VT fuse was such a potent secret that for fear of it falling into enemy hands and being deployed against Allied aircraft, its use was strictly limited to ground defense or naval operations over water until the very final months of the war.
These 5 inventions, the rugged logistical genius of the jerry can, the life-saving chemistry of penicillin, the sight-granting power of the cavity magnetron, the lethal accuracy of the hedgehog, and the electronic precision of the VT proximity fuse, share a common legacy. They were not headline weapons, but they were the quiet gears of victory. They worked outside the glare of the propaganda spotlight, solving deep, complex problems of survival and logistics. They extended the reach of Allied arms, preserved the manpower required to wield them, and fundamentally altered the balance of tactical superiority in the air, on the sea, and across the vast, unforgiving expanses of the battlefield. The war was won in the workshops, and these silent catalysts collectively ensured that the grand strategic objectives of the Allied forces could actually be achieved, transforming abstract plans into concrete battlefield reality.